And our first presenter is Dr. Steve Hoff. Dr. Hoff is a professor of agriculture and biosystem engineering at Iowa State University. And our second presenter today is Dr. Dan Andersen. And Dr. Andersen is currently an assistant professor of extension specialist in agricultural and biosystems engineering at Iowa State University. And our third speaker is Dr. Brian Kerr. Brian Kerr was raised on a cash and grain swine farm in west central Illinois. Since January 2001, Dr. Kerr has been the research lead scientist for the USDA Swine Research Unit in Ames. And our fourth presenter is Stephen Tribune. So I don't have
He's a chemist at ARS.
And he's a chemist at ARS. I didn't have a bio from him. So they'll just go through and speak, and just wait for questions at the end. And if you have any questions, thanks.
Great. Okay. Good afternoon, everyone. It's a pleasure to be here today. Purpose of this seminar is to give you a little progress and update on some of the research we've been doing on pit foaming. Basically what we know, what we don't know, and what we're doing. So, objectives, I'd like to update you on our IPPA-funded pit foaming research project. Multi-state, multidisciplinary approach to this problem, summarize some of the results that we have, and go through briefly some of the precautionary measures. Okay, so foaming. What is required for manure to foam? Number one, you basically need three things, and you need all three of them. Some form of gas generation. So we do have methane, we do have some hydrogen sulfide, so we do have some gas generation. Naturally, they release at very, very low levels, but under certain situations, if we have something on the manure that is reducing the surface tension or a surfactant of some kind, basically it kind of elasticizes, if you will, the surface of the manure and allows a bubble to form. But still, that's not enough. Once a bubble forms, you need something to hold it in place, like a dome structure. You need something to support that bubble. Okay? So you need all three things, and our research has been really geared towards all three of these components. So we've all heard stories and probably have seen a few pictures on foaming, but in some situations, it gets into the occupied zone of the pigs. And it's a situation, of course, that we need to deal with. Here's the curious nature of foaming. It has occurred in one pit of side-by-side rooms with an equalizing channel. All right? Go figure. Commonly found in one barn of multi-barn sites with common genetics, feed, management, etc. Okay? Adds to the puzzle. Attempts at correlating foaming versus non-foaming barns with multiple factors has been elusive. Some of the results that my colleagues will share with you today, we try to dig into some of these correlating factors. Let's talk about the IPPA-funded research project. Fantastic support in dealing with this issue. Our goal is to find and correct the mechanisms of foaming. We feel that if we can go back far enough to see sort of, how does foam form in the first place, the marketplace will then take over and identify some of those key mechanisms. This is a multi-state effort. We have folks from Iowa State, USDA, ARS, University of Minnesota, University of Illinois. We have over 20-plus academic professionals here from the chemistry side, microbiology side, engineering side, nutrition side. We have a very, very good team. It's $1 million investment that the pork producers have entrusted us with over 3 years. We are now just finishing up our second year. We are at Iowa State managing the project, and I can assure you our team is working very diligently to solve this problem. Again, very multi-state research collaboration. Dan, Brian, and Steve at Iowa State, USDA, looking at some feed trials. You'll see some results from that today. chemical composition analysis, methane production. Dan is going to talk quite a bit about that. And then foaming potential testing. Some interesting results there as well. University of Minnesota, they have conducted for us an extensive producer survey. They're doing some microbial analysis for us and also doing some foaming potential testing. My colleagues there, Chuck Clanton, Larry Jacobson, Bo Hu, and Brian Hetchler. University of Illinois, they basically took on the task of organizing an enormous database. We have an enormous database here, and it's taken a lot of time to really get all of our information organized to the point where we can start looking at correlations, which we are doing now. So they took on the task of organizing all of that information, and they have conducted some very interesting microbial analysis. You'll see some of those results today as well. My colleagues at Illinois, Rich Gates, Angela Kent, Laura Peppel. So with that, we're going to get into some of the results. And this is where this project manager sits down and puts the experts up here. So, Dr. Dan Andersen.
All right, so thanks for the opportunity to come down and speak. I'm going to rely heavily on my colleagues as we go through this presentation, so just a forewarning there. So a little bit on that theory. As Steve mentioned, we really need three things. We need that gas phase, a surfactant phase, and a stabilization phase. And all three legs of those pyramids, of that pyramid, have to work together in order to cause foam. If you can kick out any leg of that pyramid, chances are we could mitigate foam. So we're going to focus on describing each of those mechanisms for you and what's happening in our feeding trials, or in our foaming pit situation. All right, so as we started this, we worked on a few hypotheses of what are we going to do, how are we going to conceptualize this problem and attack it. And really, we broke it down into 4 steps as a team as we started to think about that. And the first one was understanding that gas phase. We know that the methane is important not only for the explosion potential, but for filling those bubbles and causing foam. So we really wanted to get at that phase to sort of answer the questions of why is it happening now, why is it happening at all. As we started, we were really interested in that surface active agent. What is it, where is it coming from, and potentially how could we stop it? And finally, I think that stabilization factor has been really important to us as we've concluded with our research here and moved forward. And then obviously the goal was to relate this to the physical, chemical, and biological properties resulting from different dietary inputs. I think a lot of us had a perception that feed ingredients were clearly important, and it was how can we connect these pieces of the puzzle back to what we're feeding to that animal. Going along with that, I think there was this inherent understanding that microbes had to be involved. When we see foaming in one pit at a site but not in another, that really points to some sort of variability often driven by microbes. So working with our colleagues at Illinois and at Minnesota, who specialize in some of this microbial analysis, we were very interested in getting at this picture of are there differences and what are they? And then finally, ultimately, hopefully, what's driving those differences? So as Steve mentioned, we had a pretty extensive manure collection as part of this project. On a monthly basis, we were going to over 60 sites and routinely sampling manure from them. One of our thoughts was there's a lot of variability out there. There's a lot of differences between barns, whether it be consistently foaming or not foaming, or some of these that are transitioning. And in order to understand this problem, we really had to get all types of manure samples. So what I'm going to show you here is sort of a conceptualization of how we thought of that manure. And we collected samples from various layers throughout that structure. Starting with the foam itself, we know that foam is quite unique, so we're very much interested in characterizing it and understanding it. So that's going to be our top layer there. The next one, right below that, we thought surfactants were very important. So we were very interested in what's sort of on that surface of the manure. And if you want to conceptualize it, we think of it as a credit card limit, a credit card thickness of this whatever surfactant is there that we're going to try and sample. And the way I sort of thought about it is if you're looking for a surfactant, one example you could picture in your head is sort of an oil slick on water. Well, there's not much oil up there to be found, right? You have to be very careful as you sample. So making sure that we were thorough in our sampling and trying to pick that out was important to us. And then finally, as we moved down through that pit, some manure sample, and then looking at that sludge, whether it be at the bottom of the pit or not to the level that it had been in foaming barns. So we collected somewhere around 2,000 samples of manure. So a lot of data to work with. And the good news is we got a lot of barns that were consistently foaming, some non-foaming, and then some of these transitions. So we have a nice pool, a nice assortment of types of facilities to evaluate. And what I want to point out here is we did work with 2 major integrators of swine producers, and we have roughly the same number of samples from both. So that'll give us some pretty good dietary differences as we work through some of our field study results. And I think we all know diet's important, and we were fortunate enough to have a nice nutritionist on our team to sort of help us understand some of those dietary ingredients. So I'm going to hand it over to him for a little bit here to work through some of this.
Thanks, Dan. Just to give you kind of a general synopsis of how we came to this experiment. If you remember one of Dan's comments that one thing is the biogas generation. When you look at that from an animal standpoint, the input that's going into the biogas generation is really the output from the animal. That is the manure, the urine and feces from the pig. So as we looked at that nutritionally, is what is coming out of the pig that is going into the pit. And this is just kind of a generalized example of one of the experiments we conducted for this project. And
Right there.
here we go. Thank you. So what we did, and again, kind of a generalized thought process here, a simplified corn soybean meal diet. This happens to be the composition of that diet. So ether extract or crude fat, as you might be more familiar with. NDF is a fiber component, and of course crude protein. Thinking about biogas generation, ultimately it comes down to carbon input, i.e. carbon coming out of the pig. So basically the bottom column in here is this diet has about 45% carbon coming from either fat, fiber, protein, things like that. And then nutritionally, way I looked at that and what this data worked on was we look at how much is digested in that, conversely how much is excreted. And then I kind of did this for X amount of pigs, 1,250 pigs, and then a consumption of about 700 pounds per pig, basically weaned to finish. So this would be an output, basically one turn of a building, output of fat, fiber component, protein, and ultimately carbon. One of the early thinkings was there were specific feed ingredients that were really associated a lot with foaming. Nutritionally, the way that I look at that is not a specific feed ingredient, but what that feed ingredient encompasses. So, for example, if you want to say it was related to distillers, my opinion is it's not distillers per se, it is fiber. So when you go to a higher fiber diet, whether it be wheat midds, distillers, corn germ meal, something like that, you formulate the diet a bit differently, and your output will be different relative to that diet. And that's what the second set of data here is showing. So if we go from a very simple diet, corn soy, and we go to a higher fiber diet, well, we'll have more fiber. We'll have a little bit more oil added, so we balance the energy in that to the pig. Here's what happens. Digestibility components change a bit, but just let me jump over to here. Relative to a corn soybean type of diet, our fat excretion, that is fat excretion from the pig, goes up, for example, like 35%. We don't digest all the fiber. The pig does not digest it. Tremendous increase in amount of output in that pig. So you see a tremendous amount of fiber equivalent, protein equivalent. So basically, the carbon coming out of this pig fed this type of diet is substantially more than you would see in a more simplified diet. It's that carbon, in my opinion, that is the input into the manure, which then the microbes, and Dan will talk about later, is going into that as a input into the system. Again, nutritionally thinking about that is I get down to a carbon component, and that'd be this column here. So about 30% of the extra carbon in this higher fiber diet is coming from crude fat. Basically, the proportion is greatest here for fiber. Again, fiber's not digested. That's a lot of the carbon, about 55%. And of course, some protein is dragged with that, so you see this 17%. And I think that's critical to understanding of what diet impacts might be affecting methane production and the microbial ecology of the pit. If we look across several of our trials, not just this experiment by this process, but others, when you increase fiber in the diet, basically in our system, carbon excretion increases about 40%. Again, that's about what our last experiment showed. So again, put that in your mind as we change the diet, what is the output of the pig, which is the input into the tank. And again, some of the lipids we add, the pig utilizes quite differently. So if it's lipid within the cell of a feedstuff, that's not digested as well as a liquid that you would put on there. We change the diet, we change the proportion of those. And then you have interactions between the amount of fiber in the diet, the amount and type of fiber, and the type of lipids. Again, all that affects the outflow of the pig or the input into the pit, and we think that's important. Now, what was interesting in this last trial, we did a particle size study within this experiment. So we ground it from, which would be quite coarse now, about 630 microns to about 370 microns. Grinding a feed can dramatically improve the digestibility of a feedstuff, especially if it's a poorly digested feedstuff. But what was quite interesting here, and we're going to look at this a little bit more in some experiments, was the impact on lipid and fiber digestibility. Lipids quite a bit and fibers quite a bit. So again, grinding to a smaller particle size, digestibility is better in the pig, so we retain the nutrients in the pig and we'll have less output. Again, pig output is input into the pit. And looking at a specific feedstuff, again, this from our data set, looking at a specific one and kind of stretching how I look at that data. A smaller size, particle size distillers has an improved digestibility of lipid than would a coarser size distillers.
So I think a big part of what we were trying to get at there is understanding why this is a problem now. And we think that changing that feedstuff, providing more carbon into that system, into that manure to feed our microbes, plays a big role in this. So to help illustrate this point a little bit, what I'm showing here is some data on gas production potential. So think of it as available food for microbes to eat. And this was based on a particle size diet. We had a coarse grind, that's 700 microns, and those would be there on the left, those three, and a finer grind diet, these three over here. So as you'd expect, this relates pretty heavily to digestibility. When we had coarser grind, we had less digestibility. We end up with more food in the pit for those microbes, and as a result, we feed that microbial system and can generate more gas and just more microbial activity. When we grind finer, we reduce that level. The other thing I want to point out is the DDG's diet and a soy hull's diet both added fiber to that manure. And as a result, we tend to see slightly increased or increased levels of methane potential. So that higher fiber diet tends to be feeding our microbes, more carbon in the pit, feeding microbes, more microbial activity, and potentially more foaming. So one of the things we really wanted to get at was understanding this gas phase. Is there a difference between foaming and non-foaming barns? And there really isn't a standardized test for this. There's ways to go out in the field and measure methane emissions from farms, but it's really quite involved and quite extensive and not good for surveying large number of farms. So we developed a technique to sort of answer this question of how fast are manures making methane gas. And up here I'm showing just a lab setup of what we have, but basically we can bring that manure back and measure some characteristics about how much gas it's making. The important point here is what we found is that every time we're out there, we see a lot more methane, a lot faster rate of methane production from those foaming manures than we did from the non-foaming manures. And it was very consistent in every month. So that microbial activity is a lot higher. And that microbial activity is a lot for us. That gas production not only helps make the bubbles, but it could move things around in that manure for us. So the first thing we really wanted to try and get at is why might this be the case? Why are we seeing these higher methane production rates in foaming manures? And there was a few things that we wanted to try and get at, and basically they were how much food is there, so how much carbon is in the pit, and we looked at some feeding trials for that. And then we wanted to look at sort of the source of that carbon. Is there quality differences and ways to measure that? And we also thought that microbes might be important, so is differences in microbial populations driving differences in processing? All right, so when we talk about the quantity of food, in my mind, we're really looking at two variables, but they're mostly related to solids content. So up here I have a volatile solids content, which is sort of a measure of food for the microbe, and I think that's where we'll start our focus. And we did see some differences with foaming manures being slightly higher, but it was certainly nothing to write home about. They're very similar, which probably should be expected. If we have a barn side by side and one's foaming and one's not, they have basically the same feed inputs, the same manure inputs. So it's not too surprising that they're not drastically different. When we talk about the real food that methanogens are consuming, what they're directly making from, we're talking about these short-chain fatty acids. And really, it's just the best microbe food we can have. But we saw the opposite story. In those non-foaming manures, more of that food was still sitting there, waiting to be consumed, which to us indicated that for some reason those microbes just hadn't taken off and started consuming that. The other thing I want to address just slightly on this side is one of the things we often say is foaming manures tend to be more homogeneous, a little bit better mixed. And the data that we collected on that would say that that's slightly true, but it's not that different. If we look at total solids content, it tends to be slightly higher in the foaming manures as we go up towards the top of that manure. But it's not a drastic difference. But we do see some improvement in the fluffiness or solids distribution of those manures. So since we didn't find these drastic differences in the quality of food, we thought, well, maybe there's some differences in quality. Is there certain things in those foaming manures that the microbes just like better? And one way to measure that is how much gas could they still make from it. So we did some tests on that. And what we found is, again, the non-foaming manures had more potential left to make gas. And the way we interpreted that is it just hadn't been consumed yet. We saw that the microbes in those foaming manures were really working through that carbon, consuming a lot of it to make their methane. So they had already consumed this difference. So again, not a drastic thing, but an indication of better processing of the carbon that's ended up in the pit. So since our first two indications of food didn't turn out much, working with our colleagues at the University of Illinois, they provided some very nice microbial data to look at. And I'm going to walk through the steps of what they were doing here because it's a lot of technique that goes into it. So again, we started out with that conceptual, with lots of manure samples from lots of farms. Roughly 1,000 samples go into this database, and each one of those they extracted the microbial DNA. So they could basically do a fingerprint of each manure sample. And what they generated was a data with a peak at various distances along this x-axis. And each peak corresponds to some type of microbe, right? So it's sort of a microbial fingerprinting or a census of the microbes in the manure. And then they do a little bit of math and some fancy data processing, but they can put it all on a 2D plot. And these two plots basically tell us similarity or differences between microbes. So if we see 2 points very close together on the plot, that would mean those pits had very similar microbial populations, right? The census of those two pits indicated that everything was very similar. If two samples are quite distant on this plot, so one on one side and one on the other, that would indicate big differences between those two manure samples. So different types of microbes or different numbers of those types of microbes in the manure. All right, so what they were hoping to find was a nice separation between non-foaming manures and foaming manures, right? A nice clear divide of these microbial populations are different. So looking at what the data actually looks like, we tend to see some pretty decent differences between the manures. There's a nice cluster of blue non-foaming manures here on the left, and that's pretty different than our foaming manures here on the right. So they did tend to find those differences. So we know that differences in microbial community structure have developed. On top of that, they did some sequencing data. So their first technique sort of would tell us, yes, there's generally differences in microbial community, but it doesn't identify specific microbes that might be the issue. But one thing they could do from that data is they could look at microbial richness, which I would tell you is a measure of diversity. How many types of microbes are in there? And what we tend to see is that foaming manures have less diversity than non-foaming manures. So there's specific microbes that tend to be more prevalent, more pronounced in those foaming pits that tend to be taking over. But I think an important point to make about this data is there wasn't some brand new microbe. There wasn't some new microbe that had developed based on things we'd done. It was microbes that were all present in the manure to start with. They're just present in different populations. So there's not some new Andromeda strain out there wreaking havoc on our barns. Using their sequencing data, they could look at specific microbes. And for our purposes here, I don't think it's important for us to identify these microbes and talk about them, but it's important to see that we can fingerprint which ones they were. So in some cases, different microbial species, taxa, were more pronounced in the foaming manures than in the non-foaming manures, and for certain ones, they were less pronounced, right? There was more of them in the non-foaming manures. So there's a few ways to think about this data, and one would be, as a mitigation technique, is there ways to adjust these microbial populations? So the next task is we really wanted to get at what are some of the things that we're either feeding or doing that might be influencing both these microbial community structures as well as some of the physical and chemical characteristics of the manure that we were identifying. So we tried to relate all these properties to lots of management factors. So this is real-world data, so it's not always as clean as you'd like, but it does give us some indications of what we think is happening. So again, we're looking at that microbial community structure overlay. So 2 points close together, like these two, would have very similar microbial communities, and 2 points that are far apart, such as this one and a point over here, would be quite different. And you can see some arrows overlaid on top of that plot. There's two things about the arrows that we're trying to look at. One is the direction that they point. So if you see arrows pointing in the direction of foaming, that would be indicating that that dietary ingredient is influencing microbial community structures to be more similar to manures in this area. Right? So if the arrow points in that direction, it's leading towards a microbial community similar to those microbes. The other thing that's important is the size of that arrow. In general, all these arrows are relatively short, but a longer arrow would indicate a high influence. So based on some thought and some of what our dietary ingredients indicated in our feeding trials, what we interpret this diagram to say is that the more corn that you tend to include in your diet, the less chance you have of foaming. Alternatively, the more higher fiber ingredients that you're adding, you're increasing that probability for foaming. So again, it comes down to feeding that microbial system. The second thing we tried to do is that somehow related to functionality of those microbes? For instance, are foaming microbial communities associated with higher rates of methane production? In this case, we found a pretty strong indication that the foaming manures were indeed strongly correlated to higher methane production rates, so faster methane production, as well as higher pH, which we interpret to be indicative of that manure is more processed. Some of the proteins in that manure are more broken down and resulting in a slightly more basic pH. All right, so we've started to get our fingers around this idea that these bacteria might prefer certain foodstuffs a little bit better. So one of the things we tried to do was identify if some different dietary ingredients could really increase methane production from these manures. So we fed them a series of things, including fiber, oil, proteins, sugar, and soybean hulls, which is a real-world fiber. What our data here showed is that foaming manures respond better to everything, but in particular, they really love that fiber and oil, which means they really like the soybean hulls. So again, it sort of indicates, again, those substrates that are getting into the manures. So feeding that higher fiber diet ingredients, pushing those things into the pit to feed that microbial system. All right, so we're going to switch gears from our biogas a little bit. We said that three things are really important for causing foam. One is that gas phase, and we've sort of seen that pretty consistently, a major difference. But a second one is surfactants, and we think surfactants usually are important in driving foam. But what our data here tends to show us is that there are some small differences between foaming and non-foaming barns, indicated here by the line. So the blue bars would be the foaming manures at various depths, so the surface of the manure down to deeper, and the red bars would be the non-foaming. But the differences are relatively small. The only layer we see a difference from the other layers is right at that surface. So that would tend to indicate that there's some sort of oil accumulation on that surface, and it is lowering our surface tension, but it happens in both foaming and non-foaming barns. So there's not a big difference in that surface tension or that surfactant phase between foaming and not foaming. So what that should tell us is that we don't see a large difference in the capacity of these manures to foam. If we'd come through and give them those bubbles that they need, they should both foam about as well. What we tend to see is that's the case. There isn't a big difference between foaming and non-foaming barns in their capacity to foam. But as I'll show you on the next slide, there's a big difference in their ability to stabilize that foam. So what I think this tells us is that although surfactants are important to foam, they aren't driving our differences between foaming and non-foaming barns in this case. All right, so stability, what stabilizes that foam is really important. One of the things we noticed right away when we started playing with this foam is even after we sample it and bring it back from your farms, that foam would stick around for days. And that was pretty unique. It just had this stability where it didn't break apart. So we were really interested in sort of quantifying that and understanding why that might be true. So what we're looking at here is data on how different layers of that manure foamed. So this A sample right here would be the foam itself. And what you can see is it's super stable in comparison to everything else we brought back. So for some reason, that foam has a great capacity to stabilize. And that's really unique in comparison to the manure underneath it. If we look at just that B level, since we can't compare A's, since A samples from non-foaming barns don't exist, there's no way to collect nothing, we had to look at that first interface layer, right? So that credit card layer of what's there. And what we saw is there's a pretty big difference in the stability between those two barns. So when I look at all this data, it says to me that whatever's stabilizing that foam is the critical leg of this tripod. It's really what our problem phase is. So obviously that meant we had to get to work on understanding what's driving that stability. And we did this in a couple ways. When we looked at existing literature on what makes foam stable, the first thing is you want that foam to stay really wet. As you can imagine, as the liquid drains out from that foam and the bubble wall is thin, they're more prone to popping. So keeping them wet makes them more stable. They can handle a little more air over them. They just don't break as easily. And one way to sort of get at how quickly things will drain is a measure of viscosity. So what we can see is that the foam itself was really viscous, which didn't come as too big of a surprise. We know that the foam has tons of solids in it, and solids are related to viscosity. So we started playing with that manure quite a bit to remove those solids, and we did two things. The first was we centrifuged them to get all those solids out of there. And that brought our viscosity down a lot, but we still saw that that foam is much more viscous than manure. So there's something special in it that's making it this sticky, gooey mess. So then we started speculating on what that could be. And there's lots of potentials for it. So it could be a sugar or an oil or a lipopolysaccharide or a protein. Or, as we first started out when we had less idea about what it is, this general microbial goo. All right, so what we've tended to see based on our visual observation is those particles are really important. They form that structure and hold it together. Just like Steve said, a dome needs support, and those particles are providing the support. So we tried to get at these particles and characterize them. So we did quite a bit of particle size analysis on both the foam itself and the manures underneath. And what we found was particle size between 2 and 25 microns, so roughly here to here, are really accumulating in that foam. And they're what's driving that stability. But the most important thing to me from this data is that the foaming manure itself is depleted in particles of this size in comparison to the non-foaming manure. So those particles are being lifted out of the manure and separated up into that foaming layer. And what's doing that for us is our methane production. So not only is it the gas phase to drive formation of these bubbles, but it's also bringing those particles that we need to stabilize it up to the surface. So it's involved in two phases. All right, as we've talked about a little earlier, we had those some dietary studies. And in the dietary studies we've done, we haven't been able to cause foaming at all. They've actually been some of the non-foamiest manures we studied in comparison to field. So in some ways, you might consider that not a success, right? But there's still a lot of things you can learn from it once you know what you're looking for. So we had learned that those particle sizes, 2 to 25 microns, were pretty important. So we asked some questions like, are those particles in all manures? And what you can see here is, yep, even in manures that won't foam at all and are nowhere near foaming, those particles are still present. So the other thing I should point out is this peak right here, that's related to feed that your animal excreted. These particles that we're looking at down here, they're most likely microbial particles, things that microbes are making while they break things down in the manure. The other thing we saw from this feeding trial is that anytime we ended up with more carbon in our manure, we ended up with more particles in this size range. So even though we ground coarser, we ended up with more small particles because we had fed those microbes and gave them the ability to process some carbon and make those particles we needed for stabilization. The same thing in this study, we had inoculated some of our manure. So we seeded it to make it more aged, to better build a microbial community in it. And by doing that, again, we ended up with more of these fine particles. So it's a pretty strong indication that the microbial system is naturally going to produce these particles, and they're going to be present in our manure. All right, so we had started to wrap our heads around, well, these fine particles are really important, can we do things that will make foam by adding particles in this size range? And we stumbled on a few things that we were going to try. One, we had some biochars available to us that were roughly in this particle size range. And while we were doing that, we thought, well, tannins are available. They happen to fall in this particle size range, and they reduce microbial activity. So we added some of these things to our manure to see what would happen. And I told you that we couldn't make any of our feeding trial manure make a foam. Well, this is our feeding trial manure after we've added tannins to it and aerated it with to make some bubble structure. What you can see is we made a foam, which we were pretty excited about. And not only did we make a foam, but we made a foam that was super stable and would stick around for days. It had a half-life of 4 to 5 days, which was vastly higher than what we had originally had of 2 to 3 seconds. So a pretty big difference. So we really started to get at, well, particles of this size are really important to providing that stability. Unfortunately, the biochars didn't do that for us. Despite the fact they were in that particle size range, no foam stability. So we started to research a little bit more about why that might be the case. And luckily we have a great chemist on our team who was able to point us in the direction of, well, tannins interact with proteins. So we started to get on this train of how are these things interacting with proteins to provide that stability. So here's some protein data to start backing this up. So what we're going to look at is the foam itself, foaming manure, and non-foaming manure. And if proteins are important, we'd expect to find a lot more protein in the foam, right? We have those small particles there, so they should be there. What we found was that was the case. A lot more protein in the foam as compared to the manures. And since we think it's particle related, after you centrifuge that manure to remove those particles, the difference should go away, and it did. So a particle interaction with this is really important with this protein to provide that stability. So if proteins are involved in that stabilizing process, can we remove them to destabilize it? And there's a few schools of thought on how you could destabilize proteins, but the one everyone's most familiar with probably is denaturing them. So who's ever had a hard-boiled egg? Everyone, right? It's a protein. How did you destroy that protein structure? Well, you heat it up, boiled it, and the protein unfolds, and it just doesn't look like it used to, right? So our colleagues at Minnesota did this with some manure samples. So what they did here is they did a high-temperature treatment to basically destroy that protein structure. So they heated it up to 65 degrees, and what they found is by doing so, they reduced that capacity to foam as well as the stability of that foam by 80 to 90%. So a pretty good reduction. Now I know what you're all thinking, that's not practical, we can't heat our manure up. But there are, of course, other ways of sort of breaking those proteins down. And one is through the use of enzymes. And an enzyme for a protein is a proteinase. And when they added those things to the manure, gave it a little time to react, they found that they could reduce the capacity and ability of that manure to foam by 90%. So again, pretty good news, right? We're on to something. We've decided that particles are important, and they have proteins, and we found that by adding the right probe molecule or breaking down those proteins, we can either make our manures foam a little bit more or foam less. All right, so there's one major area that we're still missing, right? What's that real thing in the real world that are holding those proteins together? So with that point, I'm going to call on my colleague to help me out. Right, this is your data. Sure. So he's sort of starting to link what some of that chemistry might be behind these proteins, or what's there in that foam that isn't there in non-foaming barns.
So microbes will form, if you're gram-negative degrading oils, you'll form lipopolysaccharides, and if you're degrading fibers, you might form exopolysaccharides. And we were just looking at the lipopolysaccharides. And so when we digested our manure, lo and behold, we couldn't find any fats, but when we digested the sugars away, we had this fat layer, and that's that top little black thing. And then when we analyzed that, it gave us evidence of a lipopolysaccharide type of material. So that was just confirmation of that material. That's all.
So really it's looking at what could be made by microbes that would be completing this part of the picture that so far we haven't found. So some good work going on there and hopefully pointing in the right direction. All right. So what do we know? Higher fiber feed ingredients have reduced nutrient digestibility and are increasing carbon in the manure. And I think that's a pretty big point. It's what's changed from 15 years ago towards times when we started to see more foaming, a lot more carbon into that manure. And that just gives us the chance to feed that microbial system and in certain cases really fire it up. So what we know is that foaming manures are a lot more efficient at processing that carbon. And you can see that based on both the lower levels of some trace molecules that microbes might be making, as well as their elevated levels of gas production. And then finally, I think we've tied that gas production into the stabilization mechanism. We can see that gas flux through the manure is bringing those small particles up and providing that stabilizer particle right where we need it, where we're forming those bubbles. Finally, the foam layer itself shows some really unique characteristics. It's solids enriched with those very fine particles that are associated with proteins. As a result, it shows that really enhanced stability. But we also know it has a lot of carbohydrates of microbial origin in it, some microbial oils, and is really viscous. So that's sort of a summary of where we're at right now, what we've learned, and the direction we're moving in. So with that, I think I'll hand it back over to Steve Hoff to talk about some safety measures and some precaution.
All right. Thank you. We never want to leave a talk without going through some precautionary measures. I think the bottom line is any attempt to break up foam will release explosive levels of methane. We've measured it and we've experienced it. Therefore, some precautionary measures to adhere to. All ignition sources off, pilot lights, welding, etc. Set ventilation we're recommending at about 30 cubic feet per minute per pig space minimum. You can achieve this with opening up your curtains, provided you have enough wind potential, or you can close curtains, use fans, and your operating sealing inlet system. Of course, make sure sealing inlets are operational. Vacate barn. Then finally, the foam and pit can be disturbed. It's just some of those measures that we certainly would like everybody to adhere to. In a 1,000-head barn, let's get an idea of what 30 cubic feet per minute per pig space is. In a 1,000-head barn, it's about 2 48-inch fans, 3 36-inch fans, or about 6 24-inch fans. We have several sources for you to take a look at some precautionary measures again. National Pork Board certainly has information. Iowa State, we have information on our website as well. University of Minnesota has information, and I didn't show it here, but the University of Illinois has some information as well.